Right, so we have the limit as x goes to negative infinity. The square root of 9x to the 6th minus x, all divided by x cubed plus 1. Okay, x is going towards negative infinity. And so the leading power in the denominator is definitely x cubed. Okay, and so the degree of the denominator is 3, and we can't match this whole degree numerator degree denominator since there's this root involved. Whether the root was over the minus x or not, it is over the minus x here. But as soon as there's square roots involved, we can't use any other shortcuts. We have to involve algebra, and so we're going to multiply both numerator and denominator by the reciprocal of x cubed. So we have 1 over x cubed to distribute through, and so on the denominator that won't be an issue at all. In the denominator we'll have 1 over x cubed times x cubed to give us a 1. In the numerator is where we're going to have our issue. The denominator is just going to be 1 plus 1 over x cubed. Okay. In the numerator though, we have to divide this root by x cubed. Last time what we did, we said, well, I'd like for it to have a root, because then if they both had a root, I can put them in one root, and then I can do my cancellation like I want to. But with the numerator part having a root, the denominator of that not having the root, we can't just do our cancellation. So last time we just said, well, let's just call it, take the thing and square it, and then put a root on it. And so we did that. It was x for our other example. This is x cubed. And so one name for x cubed is the square root of x to the 6th. So that we can incorporate it into the other root. The issue is this. Because we're now going towards negative infinity, then this x cubed here should be a negative number. Right? You take a negative number and cube it, it's negative. So that gets lost, however, when we go to rename it. If I call it the square root of x to the 6th and don't put this negative in front of it, then that's a positive number. And so, because we're going towards negative infinity, and this is an odd power, then when I go to rename it, I have to enforce the fact that it's negative by putting it there. When the last problem, we didn't even care about that. We didn't care because it was x is going towards infinity. And it was an odd power, but x was going towards infinity. Doesn't matter when you take that to that power. And so you're going to look out for this strange combination of the x going towards negative infinity together with the leading term in the denominator being odd. Okay. And so this is a lethal combination. It requires you to enforce this negative when normally you wouldn't even care about it. Questions on that? Yes?
Why don't we just forget about the negative until
We can't say these things are equal. We can't just forget about.
Yeah, but I mean, like.
We have to be formal with it. We have to say limit each time. And as we're doing this limit, we can't forget about the fact that it's negative. In the end, yes, we're going to put this negative on. I say we need to put it on now, though. You can't write this statement followed by this statement without putting the negative on there, unfortunately. So we have to be more formal with the way we write it out. Okay. A lot of times you do a problem, you end up with the opposite answer. You just say, oh, it's the positive, but we need the explanation as to why. And this is the why along the way, not just flipping it at the end to make it match the answer. Okay. It's very important that we enforce it when it needs to be enforced. Good question. All right, so now what do we do? Well, now we put them together. So we say, well, that's now one big root, where the 9x to the 6th minus the x is all divided by the x to the 6th. And so we just enforce the negative afterwards. We can cancel. We can make this 9x to the 6th over x to the 6th. And then x over x to the 6th. So that's going to be 9 minus 1 over x to the 5th. That's how that one's going to cancel. And we're setting this up to be any term that has 1 over x to a power will go to 0. We saw that on the previous lecture notes. So this is why this one goes to -3 and not to 3. Okay. So be on the lookout for that combination of x going towards -infinity and the power on x being odd. That combination forces you to employ that negative when otherwise you wouldn't care about it. All right, great. Good with that. All right, now we're going to jump to chapter 3. We talked about how if we're trying to find the slope of a tangent line, we can find the slope of a bunch of secant lines as the gap between the points gets smaller and smaller. Now we're going to formalize that, and we're going to call it a special name. So the limit of the slopes of the secant lines is the slope of the tangent line. We're going to take what we did in the first lecture, 2.1, and now what we've done since then, limits, and put these two ideas together. We were doing a limiting process. We didn't know it back then, but now that we know limits, we can put the two together. We are going to say that the limit of the secant line slopes is the tangent line slope. Remember how we had the point and they were approaching, we had one point anchored and the other point was approaching that point? Well, we're going to do that, and what we had said was this secant line slope was the difference in the y's, f of x minus f of a, divided by the difference in the x's, x minus a. So if I do a limit now, what's happening? X is approaching A. Now, from our picture, it looks like it's only approaching from the right-hand side, but we're going to say that we can let it approach from either side. Remember, there's no indication of right or left here. So this limit of the secant line slopes is the tangent line slope. Okay. Exactly, not a guess anymore. We don't have to like make some approximation. We don't have to use a calculator. This is exact now. We know exactly the slope of the tangent line by this limiting process on the slope of the secant lines. The symbol that we use for this is a prime symbol right after the function name. So f prime at a, and it stands for the slope of the tangent line. This is labeled here t. To your function f of x at the point x equals a, when x is equal to a. And so the slope of the red line is the limit. So it's a process of us finding the limits. This is one way to write it. Our book gives us two different ways. I think you'll find this way not to be the one that you end up using most often. The one that we have on the next slide is more usable. It's actually what we employ in the definition of the derivative. But this works too, though. Questions on this? The limit of the secant line slopes is the tangent line slope. Exactly. No more guessing. Okay. All right. That's out of order. Sorry about that. All right. Now just change the variables around. And so this will be the one that's more universally used. So instead of x approaching a, we'll have this this notion of, okay, yes, we still have the a, but the other point, instead of calling it x, we call it a plus h. So we move down the line some value of x called a plus h. We do exactly the same thing, though. We subtract the y's, subtract the x's, but now it's set up when we go to subtract the x's, we get that value h. This distance between our x values is getting smaller and smaller. A plus h minus a is just an h. And so when we go to set up the secant line slope, we say that we subtract the y's, so f of a plus h minus f of a, and we divide by the subtraction of the x's, which is just h. And our limiting process is as h goes to 0, as this gap between our points goes to 0 from either side. Right now, it seems like the picture just has it going from the right-hand side, but h is going towards 0 from either side. And this is the more universally used way to find the slope of a tangent line at a particular point, x equals a. Okay, it's a limit of secant line slopes. All right. So we have these two competing ways. You can do whichever one you like. I won't say you have to use one or the other. This is the one that we're gonna later use in the definition of the derivative. So I feel like you should get more used to using this one than the other one, but just know that the other one also works. Okay. Let's see some examples. Oh wait, I'm sorry. Visually, what's going on here is so don't worry about that. Basically, here's the picture. This is one of the older textbooks that we used to have. Here's the picture of what's going on. They have this technology where you can play with this picture here. You can change the graph. Here's the idea. I have a graph of a line of a function y equals f of x. I'm interested in the tangent line at a particular point, and then what it'll do for you, it'll zoom in, and what you're going to do is then recognize that as I'm able to slide this slider or whatever, I can tell that as I zoom in, this is a higher resolution zoom. Basically, what the idea is that the tangent line and the function almost become indistinguishable. And so they agree at this point of tangency. Anywhere away from that point of tangency, they disagree. But locally, nearby, they almost are one on top of the other. You can't distinguish one from the other. The further you move away, there'll be more of a gap between them. Yes, but as long as you stay nearby, though, you can't be able to, it's hard to even tell the difference between them. And so what will end up happening is we're going to use this idea to help us try to figure out, well, if I want to study the function, it'd be much easier to study the line. And so I'll be interested in trying to find a value of the function, but instead of using the function to get that value, I'll be using the tangent line to get that value. Since they're so indistinguishable, as long as I stay close, then I'll be able to say that my error isn't much at all. That's coming, but not until later on in chapter 3, though. But that's the visual of what's going on, though. This is one of the reasons why we care so much about this tangent line. Okay. Locally, they are the same. Nearby, they are the same, and we can use the tangent line to approximate the function. Okay. All right, great. All right, so here's just a thought question before we get to the calculation of some of those tangent line slopes. So we have here a graph of a function called g of x, and we have 5 different values. These are symbols. And we have to decipher these symbols and tell who's the smallest, list them from smallest to largest. Okay. So we said that if we put a prime symbol, that stands for the slope of the tangent line at that value of x. So all of these 4 are all tangent line slopes, while this one's just 0. And so we have tangent line slope at -2 and 0 and 2 and 4. Tangent line slopes. We're supposed to be able to judge who's larger than the others. And so first up, we have the tangent line slope at -2. So here's -2, and so we'll go and draw a tangent line. The slope of that line will be represented by that symbol, g prime of -2. How steep that line is will be exactly what this is. This is the slope of this particular line. That's what that symbol means. At 0, right now all we can say is that it's positive. Okay, that's about it. We don't have, later on we'll be able to compare it with one of these other guys and say, whether it's steeper or not, and that can help us decide the size of it. But right now we can just say that it's positive. Because we're comparing with 0, so if we know how it relates to 0, we can separate the positives from the negatives. Okay, the slope of this line here is a positive, and it's going to represent it by the steepness of that line. Move on to 0. Draw the tangent line in there. Come up with it's hard to tell the difference between the tangent line and the function there, but that is it, and it is a negative sloping line. So it'll be smaller than 0. Okay. Move on to x equals 2. Tangent line there. We have to compare, see who's steeper, the one or the other, but they're both positive. And then finally, the tangent line at 4. It's also positive. So we have 3 positive values, 1 negative value, and 0. So this guy is 0. This guy is positive. This guy is negative. These guys are positive. So when it comes time to list them from smallest to largest, we have to start with this guy. G prime of 0. And then we have 0. Okay, now we need to decide on, basically, relatively speaking, who's the least steep, who's the middle, and who's the most steep. Okay, so this guy's the slope of this line, this guy is the slope of this line, this guy is represented by the slope of that line, and this guy is represented by the slope of that line. Who's the least steep? The 4. So G prime of 4 would be next in our list. The most steep is at -2. The one in the middle, it's hard to eyeball it, from afar, but yeah, we'll say that's true. And so we have G prime of 4, followed by G prime of 2, and then G prime of -2. Okay, slopes of the tangent line. Steepness of the line. All right, great. Let's keep it. All right, now let's get our hands dirty with one of these calculation questions. I don't know why this thing is still up here. Oh well. So I'd like to be able to find the equation of the tangent line to the graph of this particular function at that particular point that's on the function. When x is -1, y will end up as a +3. And so we'd like to be able to find this, not just the slope of the tangent line, go a step further and find the equation of the tangent line. Okay. So we have the 2 different versions of what we would like to use. Let's go with the first version. We have the limit as x goes to a, f of x minus f of a all over x minus a. Nothing wrong with using the other version. I want you to actually get more use with the other version, but I want to at least say we use this once. And so there's the symbols for what it means. It's a limit, and in the numerator there's f of x minus f of a. In the denominator there's x minus a. And what's a? A is that anchor point where you have the tangent line drawn at. A is an x value. So for us, a is -1. That's where we're interested in having the tangent line being drawn at. So a is -1. All right, great. So we can replace the a's with -1s. And the limit now will be x going towards -1. In the numerator, I have an f of a, so that's going to be f of -1. Denominator, I have an a, so that's going to be a -1, x minus a -1. Okay. And the other symbol that I have up there is f of x. The entire function f of x would be what would go in that particular spot. So let's work it out by hand. Let me not click through this. Let's work it out by hand. So okay. When x is -1, y is 3. You can either figure it out or take this fact that it was given to you. And so that is the y value when x is -1. That is what's going to go in this spot right here. It's going to be a 3. What's going to go in this spot right here? We're going to replace it with the entire function, 2x cubed minus 5x. So we'll be doing the limit as x goes towards -1, 2x cubed minus 5x. That's the first part. And then we subtract from that the 3, and we divide by, let's go ahead and call this x plus 1. So now we're back in section 2.2 and 2.4, evaluating limits. What is the limit as x goes towards -1 of that? Now that is cubed, right? Yep. 2x cubed minus 5x minus 3. I do it this way because I want you to see how bad this could possibly get doing it this way. So we learned a bunch of techniques, and the main one was factoring. The problem with this one is that it's not quadratic. It'd be so nice if it was, instead of 2x cubed, 2x squared. I mean, not to say that thing would be factorable if it was a square, just to say that it would be nice. At least we can have a fighting chance. With the cube, where it's tough. Question? Why did I put what? Just to mess you up. Sorry. My bad. Okay. So the issue is that that's a cubic. Factoring cubics, not so easy. Factoring quadratics, not bad, but not, we like that much better than factoring a cubic. We have two options. We could know what we're looking for. Why did all those problems work out when we were factoring and canceling? The point is that we could cancel because there was an x plus 1 in the numerator to cancel this x plus 1 from the denominator. If all goes well, right, when we plug in -1, that will give us 0, right? When we plug in -1 to that function, we'll have a -2 plus a 5 minus a 3. It will give us 0. It's because this gives us 0 that we can even think of going on with this by factoring this. When we plug in -1, we get 0. It's because of the fact that it's 0 that says we have a chance. It factors. Because -1 is a 0, this is an algebra thing. When the function has a 0, then the function can be factored. It can be a factor of x minus a times whatever. So this thing factors. 2x cubed minus 5x minus 3 factors to be x minus a -1 times some quadratic. Let's call it x plus 1. Okay, how do we figure out what this quadratic is? We have a couple of options. If I want to know what this guy is, I can divide by this guy. Divide by x plus 1. That's really what I'm looking at right now. How I divide is up to me. There's a shortcut to division. See, dividing polynomials, not always an easy thing. Okay, we saw long division. Did we practice long division? I don't know for sure. Did we do this? I don't remember us doing this in our review. Oh wow, we should have. I apologize. We have to long divide, or we can do a shortcut. Nobody know what the shortcut name is? Something S. Synthetic division. Okay, let me set them both up for you. We decide which one you like. Synthetic division is a shortcut that doesn't always work. It works when the thing that you're dividing by is linear. Synthetic division works. Here's what long division is. You actually have to divide, right? When you divide with two things, one by the numerator and denominator, you take the numerator, put it on the inside, the denominator goes on the outside, and when you first learn long division, this is how you wrote it out. And now for polynomials, it's the same way. There's something we have to add in, though. We have to add in the missing terms. It's like dividing without holding the place for your place value of dividing whole numbers. You want to hold the place of the x squared by putting the fact that the coefficient on it is 0. So this is the long division way to write it out. Here's the synthetic division way to write it out. You take the thing that you're trying to divide by, basically the thing that is the root. In this case, if you have x plus 1 is what you're dividing by, -1 is the root. And some strength of the square, you can put that square if you want or not. And we're going to set up a table. What it does, it contains all the information from this long division, and it just gives you the guts of the matter. It doesn't have all the fluff that this has. Synthetic division gives you the guts, only the numbers. Okay, so here's how it works. We don't care about all these x, just put in the coefficients in decreasing order. So 2 on the x cube, 0 on the x squared, and -5 on the x, and your constant term is -3. Okay, synthetic division works. Raise your hand if you've never seen synthetic division. Okay, all right, that's all right. So here's what you do. It's a shortcut. So this process starts by you saying basically, all right, I have an x. I need a 2x cubed, so I'm going to multiply by 2x squared. In synthetic division, whatever's in this spot right here, you immediately just bring down below this line here. Okay, so we bring that 2 down, and that is going to be my coefficient on x squared. This is my coefficient on x squared. Now here's how this process works for synthetic division. Whenever you get something that's below this line, immediately above it and to the right, you multiply it by this number here, which you're saying is the root. Okay, so I multiply by -1 and I get a -2. Okay, here's what's going to happen over here. Over here, I get 2x cubed plus 2x squared. Just like when you first learned division, you had to subtract at this point. And so we get a -2x squared. That's what this is. It's hiding the math behind, it's just giving the numbers. It seems like magic almost. So we add vertically and we get the -2. That's our coefficient on x. Then we do it again. We multiply by -1 to get a +2. And we add vertically to get a -3. We multiply by -1 again. We add vertically. We know we've done it right when we get a 0 there. When you have a root, the remainder should be 0. So just, if you need more practice with this, I just would tell you to, just YouTube search it. We have plenty of videos on it. Synthetic division. And just to finish out the long division, now you have you still have an x and you want a -2x cubed, so you multiply by -2x, distribute that across, you get your -2x squared, you get your -2x, change the signs by subtracting, and you end up with, I'm sorry, I never brought down this -5x, so -5x plus a 2x is a -3x, and you end up with a -3, and which I ran out of room, but that ends up as a 0 remainder. So this hides all that. The moral of the story is that mystery quadratic that we were looking for. The mystery quadratic is exactly 2x squared minus 2x minus 3. That's the mystery quadratic that we were looking for. So now we know how this guy factors. This guy factors to be x plus 1 times that quadratic. And we can cancel now the x plus 1s. Okay, so I did this on purpose to show you how bad it could get. What do we do as soon as we cancel out the issue of division by 0? We just plug in. You plug into what's left over. Plug in x equals -1. Oh wait, I'm sorry. Oh my gosh, what is wrong with me? What was this? 2x minus 2x minus 3, sorry. 2x squared minus 2x minus 3. There we go. 2x squared minus 2x minus, that's what this guy is? Okay. All right, so plug in a -1, and what do you get out? -3. Take your time. 2 times x squared is 2. -2 times -1 is plus another 2. Then we take away 3. The answer is 1. The answer to this question is 1. The slope of the tangent line is 1. Okay. Nice visual. I'll show it to you. This is a cubic, and it has a tangent line at that particular point with a slope of 1. They want us to go a little further here and find the equation of the tangent line, but that's just algebra. We'll do that. But I just want to make sure we understand. And I'm sorry we had to do this diversion. We should have done that in our review. I apologize. That should have been done in the review. Long division versus synthetic division. And synthetic division works when you divide by a linear term. when this is linear mx plus b looking, then we can use this shortcut to long division. It might come up later in the semester where we need to actually do long division, where we divide by something that's not linear, divide by something that's quadratic or something higher. But yeah, so all that algebra was required to get this problem. And our main issue, the reason why we needed all this algebra is because we chose to use this form. If we choose to use the other form with the h, this algebra won't be necessary. In fact, I'll probably end up showing you the other way to do it. I want you to appreciate the better way, I think, by showing you the worst way, even though it wastes 20 minutes in class. I don't mind. Okay, so let me erase all this ink that's on here and just show you the animation there. So it works out synthetic division, and we end up getting the answer of 1. So now we need to find the equation of the tangent line, equation of a line, that's mx plus b. We have the m, and we have the point. So it's just an algebra question. The calculus is over. This here was the end of the calculus. What's the symbol? The symbol for this guy is exactly f prime at -1, or y prime at -1. That symbol, that dash there, we call it prime. The derivative, the slope of the tangent line at that particular x value. All right, at the end of this is just algebra. Whether you like, point slope or slope intercept, it's up to you. So I'm going to use slope intercept. So x is -1 and y is 3. So if I'm plugging the slope intercept, we have mx plus b. So the only mystery then is what the b is. I know the mx and y, and I can find out that the b is a 4. So the line is x plus 4. And I think I have a graph of it here. There's a picture of it. It's exact. No more guessing. No more stepping, away from the point, getting closer and closer and closer and saying, well, it looks like this. No more of that. We know exactly the answer. Okay. We'll come back to, remember that one where we actually did this closer, 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 stepping closer and closer? That function was x over x plus 1. We'll come back to that. We don't know how to take the derivative of that yet. We'll learn a technique to help us with that called the quotient rule, to take the and find the slope of the tangent line on that one. We'll come back to that one, but for now, we're just introducing the idea here, and this is one way to do it. I want to also show you the other way. Any questions about this way? All right, let me show you the other way. Let me just take what we need here. The other way is the limit as h goes to 0, f of x plus h, oh wait, yeah, I'm sorry, f of a plus h minus f of a all over h. This gives you f prime at a. And algebraically, it's just much easier to deal with. Okay, so let's immediately put in its place. All the a's will replace with -1s. Well, I can't say much easier. It is easier. So we have -1, replacing all the a's. I'm sorry. All right, now let's go figure out what is f at -1 plus h. We need to go figure that out. We already know f of -1. We know that's a 3. So we have to go figure out what is f of negative 1 plus h. Let's go figure that out. Oh, it is here. Okay. It's on the next slide. Okay. So, so here's the formula. Replace it with negative 1s. What does it mean to take negative 1 plus h? Replace the x. Remember what the function is. The function is 2x cubed minus 5x. So every place we see an x, we have to put negative 1 plus h, and it's very necessary that we use parentheses. If we don't, then the 5 will be distributed wrong, and the cube will be distributed wrong. So this is very necessary. And how do we work out the cube on this? Don't just cube the one and cube the other. Don't think that you can just distribute this power. Now you have to write it out. Multiply 3 copies of it. And so here's multiplying 2 copies of it first. And then here's this technique that you can use to multiply a trinomial times a binomial. Use it like a table and do a bunch of single multiplications, and then add the terms that are alike. Anyway, this is what we get by cubing negative 1 plus h. Okay, you don't have to do this, but it helps though. And so some students showed me that last semester. All right, so we get exactly that, 2 times that, minus the 5 times that quantity, negative 1 plus h. So go ahead and distribute that. So we get the plus 5 minus 5h. Distribute the 2. And we end up with 2h cubed minus 6h squared plus 6h minus 2. And what's going to happen is we get cancellation. So the minus 2 plus the 5 combine to give me a 3. And the 6h and the minus 5h combine to give me an h. What am I supposed to do with that? All of that will take the place of this part of the numerator. From that I subtract f of negative 1, which is 3. And so when I go to subtract 3, it cancels out the 3. You know you've done it right when what's left over has only h's in it. Because what are you supposed to do? You're supposed to be able to cancel this h. The only way you're going to cancel an h is if everyone in the numerator has an h. And so you know you've done it right when these two cancel here. And now you factor out the h and cancel. Immediately plug in the fact that now h is 0, and you get the value of 1. So maybe this wasn't the best example to show the difference between them, but this is the way we would normally do it, because this leads to, what if I want to do this again at some other value of x? If I can do this one time through with x in place of negative 1, then I would have a formula for the slope of the tangent line. I can plug an x in and it can spit out the slope of the tangent line. And so it's leading to the definition of the derivative, which uses this form where the a's are replaced with x's. Okay. Questions on doing the problem this way? And I want you to get used to doing it this way. Not that the other way doesn't work. It's just usually it ends up something more difficult algebraically. All right. All right. It's called a difference quotient. The first way we did it and the second way we did it, they're both called difference quotients. This is, we had it as f of x minus f of a all over x minus a. It's called a difference quotient. So if you ever see that word used, then they're just talking about trying to find the slope of the secant line. Okay? We saw in section 2.1 that secant line slope is an average rate of change, and tangent line slope is an instantaneous rate of change. So when you do the limit on the average rate of change, what you end up is is with the instantaneous rate of change. So as soon as you throw a limit on here, then what you get out is the instantaneous rate of change. That's our velocity question tied into our tangent question from section 2.1. Now with particular symbols that we can, utilize. Now that we know what a limit is. Limit of a secant line slope is a tangent line slope. Secant line slopes are average rates of change. Tangent line slopes are instantaneous rates of change. Same things we were saying before, now with different symbols, because we are now more sophisticated. We know what a limit is now, how to evaluate in certain cases. Okay. All right, I'm going to save that slide for next time. Let me go back, go to the next slide. So what I was saying was that instead of having the A in there, what if I want to go to a different value? I have to go through all that work all over again for a different value. That makes no sense to have to continue to do that each time you have a different value of x equals A. So instead, what you want is the ability to be able to have a formula where I can plug in any A I want, and in that formula, I'll be able to spit out exactly what the tangent line slope is. So replace the A's with X's in the H version of the limit. Okay. So now it's a function. The derivative, this symbol here is the slope of the tangent line. Now we're going to call it the derivative when this limit exists. It's called the derivative. It has this symbol, and it is itself a function. It takes the same x inputs and spits out the slope of the tangent line instead of spitting out the function value. It's called the derivative of our function. So the slope of the tangent line is the derivative. If you learn nothing else in this class, you'll for sure know that. Okay? This limit might not always exist, but when it does exist, then the function at that particular value of x is called differentiable. Just like we have continuity, then the ability to say that a function is continuous, then differentiability is the ability for a function to be to have a derivative that exists. What does it mean for it not to exist? For you not to exist, there must be some certain things that happen with your function. You can be differentiable at a point or differentiable at a whole bunch of points, an interval of points. And so here's what it looks like to be not differentiable. And we'll end on this note. Okay, if you have a corner, if you're looking at the graph and there's a corner, be it a sharp point or what we call here a cusp, C-U-S-P. If your graph exhibits any of these behaviors, this is called a cusp. It could be like the absolute value of x, but it has a sharp corner where it's lines meeting. It could be curves meeting at a sharp point. But anytime you have a sharp point like this in the graph of the function, then your function is not differentiable there at that value. If your function has a jump, basically any type of discontinuity, if your function is discontinuous in any kind of way, then it doesn't have a chance to be differentiable. So any type of discontinuity, not just a jump, any type of discontinuity will lead to a place where your function is not continuous. And then lastly, if your slope of your tangent line, if your tangent line ends up vertical, this is a vertical tangent line. Vertical lines have no slope, undefined slope. And so if that's the case, I'll show you an example of that. If that's the case, then you're not differentiable there either. Let's go ahead and end for today. I'll see you guys on Wednesday.